and welcome to Week 6, Lecture 1 of CO 442642 Graph Theory. Today we'll be discussing minors. So what is a minor? Maybe you're used to this definition, but we'll go through it. We say that a graph G has an H minor if a graph isomorphic to H can be obtained from a subgraph of G by contracting edges. So you know what subgraphs are, where you're allowed to delete edges and vertices, but here we're also allowed to contract edges. So identifying the endpoints of an edge to one new vertex and simplify. So here's a picture. So here I'm going to delete, so I have a 5 cycle plus a pendant vertex. I'll delete the pendant vertex, that will leave a 5 cycle, and then I'll contract the two red edges in the picture, and what we end up with is a triangle. And so therefore we'd say that the graph on the left has a K3 minor, or a C3 minor, equivalent graph. So that is what a minor is. We're allowed to not only pass to a subgraph, but contract edges. And we could contract more than just, one edge, we could have many edges. So what is a better way to think about minors is as models. So what is a model? Well, let H be a graph, this graph we want to find as a minor, and let's enumerate its vertices as V1 up to Vt. Then a model of H in a graph G is a collection of vertex disjoint connected subgraphs, H1 up to Ht, such that for every I not equal to j in T, with Vi, Vj in E of H, Hi is adjacent to H. And what that means is there is an edge with one end in Hi and the other end in Hj. So basically this tells you where to find the minor. So remember the picture from last slide where we created a K3 or C3 minor. So how would you find a model back? Well, you invert the process. You pull back. So here's the pullback of kind of the operations that led us to that minor. So here, if we enumerated the triangle as V1, V2, V3, then we'd have H1 and H2 and H3. And you can see that because when we find the final minor, we find the edges for H, there must be some edge with one end in Hi and the other end in Hj. Thus, it's not hard to see that G has an H minor if and only if there exists a model of H and G. Indeed, it's kind of the pullback or the inverse of this contracting operations. So that's two ways to think about minors. We'll be spending the next couple weeks talking about minors, this very fundamental graph theory idea. And what's going on is that, one way you think about it is how do you get other graphs as something more than subgraphs via operations. That's the first definition. The second one more says something about finding structure in a graph. Can we find lots of connected subgraphs where they have these adjacency properties? So if you wanted to find complete minors, it'd be finding lots of connected subgraphs that are pairwise adjacent. And both are useful ways to think about minors. So besides minors, though, you might also have been used to subdivisions, if we learned Kuratowski's theorem. So we say that a graph G has a subdivision of H, also known as a topological minor, if a graph isomorphic to H can be obtained from a subgraph of G by suppressing vertices of degree 2. And so suppressing just means you kind of unsubdivided them, you contract away an edge incident with it, whichever way you want to think about it. I won't draw a picture, you've probably seen this, but that's a subdivision of H. So it's also known as a topological minor. And it's a very certain special kind of minor. So actually, if you contain H as a topological minor, then you contain it as a minor, not necessarily vice versa. So that's, again, the operational definition of subdivision. And we won't be talking about subdivisions too much in this class, so I'm just bringing it up now. We'll come back to it a little bit later in the class. Mostly we'll be talking about minors. But this is the operational definition. What is the more constructional definition? Well, equivalently, there exists an ordering V1, again, up to VVH of H, distinct vertices U1, UV of H. So you map the vertices of H into distinct vertices of G, and then you find collections of paths, Pij, where Vi, Vj is in EH, and where the ends are Ui, Uj, and these paths are internally disjoint. So you can actually kind of find it topologically as an embedding. So you can embed the vertices, and then you could also embed the edges as kind of internally vertex disjoint paths. So that's the way to view subdivisions, and then in a more construction sense. So these are obviously equivalent. So then, why did I bring up subdivisions? Well, you might have heard of the famous Kuratowski theorem, which we cover in 342 from 1930, which characterizes when a graph is planar. So a graph is planar if and only if it does not contain K5 or K33 as a topological minor. So we know that K5 and K33 are not planar. There's some easy arguments to make to see that. And then actually, if you contain them as topological minors, you also want to be planar, because planarity is preserved under topological minors. And it turns out these are the only reasons. And that's a very nice theorem. We won't do the proof in this class, but you can read Diestel. But it's very nice because it gives a good characterization of planarity. Why? Well, to see that a graph is planar, I would show you a planar embedding, right? How do you convince someone a graph is not planar? Well, this theorem really tells you that way, because I can show you either the sequence of operations to get to K5 or K33, or more that set of paths with the branch vertices and the paths to show you exactly where this topological minor lives. And so it can be verified in polynomial time. So this kind of theorem shows that actually planarity is in both NP but also in co-NP, and thus is a good characterization. That's about topological minors or subdivisions, but actually Wagner showed that Kuratowski's theorem is equivalent to the following theorem, that a graph is planar if and only if it does not contain K5 or K33 as a minor. And that just kind of is coincidental circumstance. So in some sense, topological minors and minors are related, but it turns out, yeah, that so one direction is kind of obvious implied, but the other is not too hard to work out, and so Wagner showed that. And so if you want to think in terms of minors instead, that is useful. And actually, you'll see why it is better to actually think in terms of minors than in terms of subdivisions for reasons to come. But okay, so we have Kuratowski's theorem, and it's very nice because we have a fundamental class of graphs, planar graphs, and it characterizes very nicely when you're not planar, thus giving good certificates. And so what's the point is that planar graphs are a minor closed class of graphs. So we say a class of graphs G is minor closed if every graph in G, and if you have a minor h of the little g, then h is in the class. So that means that it's closed under taking minors. And indeed, planarity is like that. We knew it's closed under a subdigraph, but if you contract two adjacent vertices, you can kind of maintain the embedding. So that's why it's natural to look at planar graphs via minors, but actually then, if you have this understanding of minors and your minor closed class, you can look to the minor minimal graphs that are not in G. By minor minimal, I mean the ones that are not in G, and any proper minor would be in the class. These are called the forbidden minors of G, and they're also known as Kuratowski sets. So what's the point then? Well, maybe we can characterize this class by its Kuratowski set. And indeed, that is what we're doing, right? Is we're characterizing by the Kuratowski sets. All right, so then what's some fundamental questions? So here are two fundamental questions. For what minor closed graph classes G is the Kuratowski set finite? And a different kind of question, what is the structure of graphs with no KT minor? So, Kuratowski had this nice theorem, and it's nice that there's only two of them, so you can kind of really get a nice characterization. Is that property true for all minor closed classes? Or if not, for which ones? And what is, let's also maybe talk about the structure of forbidding certain minors. So we could talk, say, a certain planar minor, etc., but maybe more generally, let's talk just for the complete graphs, because it would give you a sense for all graphs. So we'll revisit these questions a bit later, but let's dive into some of them. So let me mention maybe some minor closed classes. So what are some other properties that are minor closed? So maybe pause and think for a moment yourself of the list of properties you know that are minor closed, and then we'll pick up. So what's one obvious one is being a forest is a minor closed property. Now what is the Kuratowski set for that? It's K3. So if you forbid having K3 minor, then you get the set of all forests. Here's one maybe you don't know, is outer planar graphs. So what is an outer planar graph? Well, it's like a planar graph, but a graph is outer planar if it can be embedded in the plane, but with all vertices incident to the infinite, or also called outer face. So all vertices are outer. And it's a nice rich class of graphs, a little easier to understand than planar graphs. What are its forbidden minors, though? So you could think of some graphs that are not outer planar, but what are the minors for it? Well, it turns out very nicely it's K23 and K4. So K4 you can't embed with all vertices in the outer face, and K23, same idea. And so it just happens to work nicely that they're kind of the Kuratowski set for planar graphs less a vertex. All right, so then what else? Well, projective planar graphs, actually. So if you go to surfaces and you want to do embedding, we saw on planar that they're closed under minors. That's true for projective planar as well. And what are the forbidden minors of the projective plane? Well, that's a lot harder. So you can get various things. For example, you could have the disjoint union of K3s and K5s, or if you kind of glue them on one or two vertices. But there's other weirder graphs that show up. So there's 35 of them in total, and this was done by Archdeacon in 1981, who was able to show that this is indeed the list by some extensive topological graph theory arguments. Okay, so that's more heavy duty. What other classes do you know about? Well, I just hinted at one. There's the graphs embeddable in a fixed surface, sigma. So all surfaces embedding on, the torus, the double torus, those are all will be minor closed, and so they would have lists of forbidden minors. What are they? Well, for anything beyond the projective plane, we don't actually know the full list. So for the torus, it's at least somewhere in the thousands, and just kind of grows exponentially with genus after that. Because you can, of course, take kind of this ones from smaller surface and kind of combine them in simple ways. But then there's also just become more and more exotic ones that would have to be found. So no one's actually proved even the list for the torus. But as we'll see, because this is minor closed property, it will be finite by a very deep theorem. But this you could actually prove individually, that they are finite lists for the surfaces. What's another one? Well, here's, a stranger one. So far we've done kind of embedding with the plane and outer plane and surfaces, and okay, forest was kind of a cheat. But here's one, linkless graphs. So we say a graph G is linkless if G can be embedded in R3, so that's 3 space, such that no two vertex disjoint cycles of G are linked. So what do I mean by linked? Well, here's kind of a rough picture of that. You could imagine having 2 rings and them being linked. So we want no 2 cycles to be linked. So all the cycles are linkless. Now you may not know that every graph can be embedded in 3 space. So that just works for every graph. So somehow, we can't, that's why we study surfaces, because they're more restrictive. 3 space, automatically all graphs become embeddable. But actually this linkless is very nice, because it turns out not all graphs can be embedded linklessly. So for example, K6, strangely the Peterson graph, and many other graphs cannot be embedded linklessly. And you can think for a moment, but linkless embedding is a minor closed property. Why? Well, deleting edges and vertices won't create links, and also contracting won't create new links, right? If 2 cycles were linked before, they would have to be linked before you contracted, if you got linked ones after contraction. So what are the forbidden minors for this? Well, it was an open question for quite a while, Sachs linkless conjecture. This was solved by Robertson, Seymour, and Tymas in 1995, and it's the Peterson family. So it's 7 graphs, which includes Peterson and K6. It's really all the graphs you can get from Peterson by the so-called delta Y operations, where you exchange Y's, which are vertex with 3 neighbors, into triangles. So you delete the vertex and you make it into a triangle. Or vice versa, it's inverse. One's coming from K6. So that's very nice. It's a series of 3 or 5 papers, 50 plus pages of proof, so we won't do that. But just showing you the complexity. So people have been studying these very nice minor closed classes, trying to establish the forbidden minors, but there's not that many theorems we know of which really establishes. So there's a number of them, but for the infinite possibilities, not so much. But we do know something for small complete minors. So let's go through that. So what's the structure of forbidding small complete minors? Well, I'll let you work through it. Let's do them together. So what happens if you forbid K1 as a minor? What do you get? Well, if you paused or thought about it for a second, it's the empty graph, obviously, is the only thing you can get if you don't have any vertices. What about K2 minors? So pause and think about that one for a moment. Well, they have a nice structure. They're independent sets, right? They're the set of independent sets of vertices. Then we keep going. We know K3 minor, we already mentioned this. Of course, you get the forests. But what is the structure of K4 minor free graphs? So what happens when you forbid K4 as a minor? That one you might not know. It's a little less obvious. So to tell you, I'll need a definition. So here's a nice definition. A K-sum of two graphs G1 and G2, here's what you do. You identify vertices of KKs in each graph, and you possibly delete the overlapping edges. So I won't draw you a picture, but imagine you have a G1 and a G2, and they have two cliques of size K. You'll identify the vertices in some ordered fashion, and then you can keep the clique, or you could delete some of it in the resulting graph. Okay, so that's called a K-sum. And actually, if you back up and think about the minor characterizations above, they actually have a nice pattern in terms of sums. So for example, K2 minor is actually the zero sum of copies of K1, right? So you're allowed to just take disjoint, zero sums would be disjoint unions, and so it would be the disjoint union of copies of K1. You might not realize it, but forests follow a similar pattern. They're taking essentially less than or equal to one sum of copies of K2, except I have to say subgraph because I have to also allow K1, or I could say K1/K2. But if you take the, it turns out forests are the subgraphs of at most one sum of copies of K2. So we have kind of zero sums of copies of K1, one sum of copies of K2. This may be an easy way to remember what the K4 structure will be, which is that if you have no K4 minor, you're a subgraph of an at most two sum of copies of K3. And again, we allow subgraph to pass down to K2s and K1s, etc., and to delete edges and such. So what does that mean? Well, these are also called series parallel graphs, if you haven't heard of that. So basically, you can create these kinds of graphs by taking kind of two operations, doing series, or where you subdivide, or parallel, where you add. And if you think through it, that is equivalent to this subgraph definition. Okay, so how do we prove that? Let me just run through a quick proof. So proof, think for yourself how you would prove this. Well, maybe the easiest way is just inductively, by induction. And to kind of go through our normal thing, a la Brooks and stuff, of using connectivity. So if you haven't seen this before, you could say, well, what happens if you have an at most one cut? So if you're disconnected, well, or if you have one cut, what do? Well, if you're disconnected, then just by induction, the components would have this property, and then you can sum them. And the same for one cuts, then you just be at most one sum of G1 and G2. So that's good. What about a two cut? Well, let's think for a moment. That's slightly harder, but then G is the two sum of G1 plus UV and G2 plus UV, both of which are minors of G. So to make it a two sum, I have to restore the edge if it wasn't there. But luckily, then if we're actually connected, then these would be indeed minors, because there would be a path from UV both in G1 and in G2. So therefore, I would know they're both minors, so they wouldn't have K4 minors, so inductively they would have this subgraph sum property, and then I would be summing them together. And then what do you do if you're three connected? So maybe you saw this exercise before in undergraduate graph theory. So what do? Well, one way to do it, if you just argue that you contain a K4 minor, and one way to do that, you could take an induced cycle C, so we're three connected, so obviously there's some cycled, so there's some shortest one, which would be induced. And then since that would have only degree 2, and we have min degree 3 since we're three connected, there have to be some vertex that's not in C, and then we could, by three connectivity, get three paths from V to C, which then forms a nice K4 minor. And of course, equivalently a K4 subdivision because it's a cubic graph. And this concludes then our proof. That would be a contradiction. So K4 minors have this very nice structure, right? So they're a nice class of graphs in themselves, and we'll revisit them in next class actually. But then what? So, we've proved this nice theorem. For example, a nice corollary is they have a vertex of degree at most 2 always. But what is the structure of K5 minor free graphs? Can we keep going? Well, so maybe stop and pause and think for a second. What is the structure? Well, it's much more complicated. For those who are tempted to answer, well, okay, shouldn't it just be like the subgraph of a threesum of copies of K4? Well, no. Why? Well, it includes all planar graphs, right? You should remember Kuratowski's, right? Planar graphs do not have K5 as a minor, so all of a sudden we get this very rich family of graphs, right? And planar graphs, they don't follow just from some kind of sum from small graph operation, unfortunately. They're a much wilder class of graphs with structure. Basically, the best way to describe planar graphs is to say that they're planar graphs, or to give their minor characterization. But if we're trying to then find a minor characterization for K5, we can't really do better than planar graphs. Except, are we done? Is that all? Is it just planar graphs? So again, stop and pause and think for a second. The answer is no, because think even Kuratowski's, obviously K33, right, would have to be K5 minor free for that characterization to make sense, so we should include it. Is that all? Well, no, there's even a supergraph of K33 called, we'll call it V8. It's the Mobius ladder on 8 vertices. Here's a picture. So this contains K33 as a minor, actually. So essentially a supergraph is just made a minor. But, so we would, if you look at V8, though, actually, if you go through it, it also doesn't have K5 as a minor. There's just kind of not enough there to contract down. And it's also nicely not planar because it contains a K33 minor. So, is that it? Is there more? Well, almost. Basically, the thing is, now you have planar graphs as the main ingredient. It turns out V8, and then this very beautiful theorem of Wagner from 37 characterizes no K5 minor. It's if and only if G can be obtained by at most 3 sums. So again, that at most 3 sums show up of planar graphs in V8, the Mobius ladder on 8 vertices. So, you would have liked 3 sums and copies of K4, but here we have to allow all planar graphs, and then we even have to throw in this V8 as a kind of the one exceptional non-planar graph. But that is actually, so this is a very nice characterization use kind of Kuratowski as some black box, and then you have this nice characterization for K5 minors, extending that beyond planar. So the 3 sums kind of make sense because maybe then you can't really find a K5 minor, but if you kind of can't get to the V8s with the 3 sums. So that's our introduction to minors. We went through we talked about Kuratowski set. We went through these 2 questions a bit. What's structure for small minors? It gets more complicated for K6 and beyond, I hope you can imagine. As, for example, K6 would already include all the linkless graphs, which are an even richer class of graphs. And there's even more. So it's hard to come up with good characterizations. But as we'll be talking about in a couple weeks, there's kind of a very nice, rough, complicated but characterization by Robertson and Seymour called the graph minor structure theorem that gives us the rough structure. And then we'll be finding out that they also answered this question about, are there finite Kuratowski sets? And the answer is yes for all graph classes. But that's what we'll be doing next time. So until then,